All right, welcome back to another explainer. Today we're diving into a massive, frankly infuriating roadblock in modern software development: how to fix flaky AI testing pipelines. As AI agents move from simple code autocomplete to actually navigating IDEs and browsers on their own, our traditional ways of testing them are just completely breaking down. Let's just jump right in with a quote from our source that I think perfectly nails the paradigm shift we're looking at today. Modern software testing is built on a fragile assumption: correct behavior is repeatable. For deterministic code, sure, this holds up. But for autonomous agents, like a cloud agent working its way through a UI, that assumption completely shatters. Here's our roadmap for today. We'll be hitting the agent trust gap, why rigid scripts fail, moving from scripts to graphs, how Dominator analysis works, proving the trust layer works, and finally, the future of AI agents.
Section 1. The Agent Testing Trust Gap. The Testing Challenge.
Okay, let's start with a scenario literally every developer knows. It's Tuesday, your build is perfectly green. Wednesday, it's red, and absolutely no code changed. So why does an AI agent actually succeed at its task, but the test still fails? Well, imagine a tiny bit of network lag on a hosted runner makes a loading screen hang for just a couple of extra seconds. The AI agent? It handles this perfectly. It waits, it adapts, and gets the job done. But your automated test completely panics and flags the run as a failure. Why?
Well, this reveals the core disconnect. The agent didn't fail at all. It's the test validation that failed, simply because it was expecting this super rigid sequence of events. It wanted the exact timing, the exact sequence of screens from the last time it ran. The agent did its job and adapted to a non-deterministic UI variation, but the pipeline failed just because the execution path took a tiny detour from the script.
And honestly, this false failure creates what we call a massive trust gap. It boils down to 3 recurring nightmares for DevOps teams. First, you've got false negatives. The task succeeds, but the runner fails anyway. Second, fragile infrastructure, where you get failures due to totally irrelevant rendering noise. And third, the compliance trap, where a perfectly correct outcome gets flagged as a regression just because the agent took a slightly different path to get there.
Moving on to Section 2, why rigid scripts fail, why our current tools break.
Whether you're using record and replay tools, visual regression testing that just compares isolated screenshots, or even manual assertion-based testing, they all break down for the exact same reason. They assume a perfectly stable, linear path for a system that is intentionally designed to not be deterministic. And look, even trying to use machine learning oracles to fix this fails because those are basically black boxes. They need thousands of training examples and give you zero explainability when they flag an error. The reality is, correctness is just no longer a single, repeatable, linear sequence. Which brings us to Section 3, moving from scripts to graphs, building a new structural model. To fix this mess, we have to completely rethink how we define correct behavior in our tests. Instead of writing these brittle, linear scripts, we need to model behavior structurally, using a graph. Enter the prefix tree acceptor, or PTA. Rather than looking at an execution as a rigid list of commands, think of it as a directed graph. The nodes are observable states, like what is actually on the screen, and the edges are transitions, like clicks or API calls. In this kind of model, paths can split apart and seamlessly rejoin without automatically failing your test. What I really love about this model is how it naturally separates the must-have milestones from all that incidental environmental noise. Like, a loading screen might pop up, or it might not. That's just an optional variation. But reaching the search results in VS Code, that absolutely must happen. The PTA graph actually lets us map out where these non-deterministic paths branch off to handle a loading spinner, and exactly where they converge back to the primary task. All right, Section 4, how Dominator analysis works, extracting the skeleton. So what's the actual technical magic that lets us extract this skeleton of truth from a bunch of different valid agent paths? To figure out what's essential versus what's just optional, the researchers applied a concept straight from compiler theory called Dominator analysis. Mathematically speaking, in a control flow graph, node A dominates node B if every single successful path from the start to B absolutely must pass through A. By calculating these relationships, we can mathematically prove which nodes every successful execution has to hit, and we can just completely ignore the optional noise. So here is the incredibly clever 3-step workflow that builds this trust layer. And the best part? No massive manual test configurations required. First, capture. You just take 2 to 10 successful execution traces and convert them into graphs. Second, generalize. The system merges these traces into one unified graph. It uses really fast visual metrics to catch identical states, and then brings in a multimodal LLM defensively to figure out if subtle UI changes actually mean something semantically different. Finally, extract. It applies that Dominator analysis we just talked about to find those essential, non-negotiable milestones. Once you've built this ground truth graph, testing new agent runs becomes unbelievably robust. Validation literally just becomes a process of topological subsequence matching, which is a fancy way of saying if the agent takes a weird detour, uses a different keyboard shortcut, or hits a random pop-up, the test still passes. As long as it eventually hits those essential Dominator nodes in the correct relative sequence, you're good. All those extra states, they're just treated as incidental noise. Let's hit section 5, proving the trust layer works, proving the framework. Now check out these numbers from a custom VS Code extension test suite. This really highlights the danger of asking an AI agent to basically grade its own homework. Look at the CUA, or Computer Use Agent Self-Assessment numbers. It had a recall of just 60%, but the PTA Dominator tree method, it hit 100% across the board in differentiating successful executions from actual bugs. It completely eliminated false negatives by focusing purely on whether those essential milestones were reached. But what you really need to take away from this data is that the agent's internal self-assessment scored literally 0% in identifying not-a-bug scenarios. 0. Agents simply cannot reliably grade their own homework in environments that constantly change. The independent trust layer, on the other hand, hit an impressive 52% F1 score on this exact same metric. That drastically reduces the mind-numbing manual review time developers waste chasing down flaky test results. Finally, Section 6, the future of AI agents. Verifiable autonomy. By moving our source of truth away from an agent's internal logic and onto a learned external structure, we are finally ready to talk about production infrastructure. Now, while this is a massive leap forward, there are still a few limitations. Right now, it does require 2 to 10 initial successful traces to learn from. It can't just learn from failure logs quite yet. It also leans on multimodal LLM APIs for some of that semantic checking. But the path forward is super exciting. Researchers are already looking into temporal constraints, like literally enforcing that a loading screen must resolve within 5 seconds. And they're implementing real-time online learning, so this structural graph just continually improves itself with every single run. As autonomous systems scale up and start doing real, complex work in our environments, we have got to stop relying on rigid scripts that break the second the wind blows. By understanding the core skeleton of a task, we finally give developers the transparency they actually need. Think about it. We shouldn't need a black box model to judge another black box model. So I'll leave you with this. Are you ready to stop letting AI grade its own homework and demand structural guarantees instead? Thanks for hanging out with me on this explainer, and I'll catch you in the next one.